Hello! Today I'm going to be solving a problem that I've been having for a while. You can see in my lab there's LED lights, and I actually have them strung up around my room as well. Um, I like the soft light it gives, especially like in the evening. But at night, I like to sleep with all the lights completely off. I have blackout curtains and everything. And these LED strips have a bit of leakage current. So even when I turn them off, I can still see them when I'm in my bed. So what I normally do is, I'll show you. So back behind my desk in the corner, I have the LEDs powered to this power strip. And what I normally do is I press this switch, which will get rid of the leakage current because that way it's not connected to anything. I am getting tired of every night having to squat down. My desk is pretty low, so I have to really get underneath there and press it. I'm kind of tired of doing that, and you may have noticed the servo motor. That's actually what this project is I'm going to set up a switch on top of my desk that I can press to toggle on the power switch of the power strip. That way I don't have to keep going down there. Okay, so to go over the servos I'm going to be using, I picked these up off of Amazon. Here's the packaging for them. And the way they work is it comes with 3 pins, black, red, and orange. Black and red is just power, which is around 5 volts, 6 volts. In the orange, it expects a specific frequency of pulses in order to move. So right now I have this actually hooked up to a signal gen up here, which is outputting a square wave of right now 0.36 kilohertz. And what happens is if I start varying this frequency, we'll see the servo starts to move. I'm going to be controlling it with a microcontroller, and actually I'll just go over the circuit I'm going to be using now. Okay, so I drew this one up ahead of time. I was working out the details of it earlier, and I have all the values, I just didn't want to erase it. So starting on the left side, I have 4 AA batteries, which will add up to be 6 volts. I have a switch right here, it's hard to see. Because it's battery power, it's important to cut it off so I don't drain the batteries if I'm not using this. That feeds into this section here, which is the 5 volt regulator. And how I'm doing that is, I'll draw this up actually on a separate circuit. Bit of a spin. Okay, so this is the same circuit from earlier, I just put it by itself. And first, I'm going to explain that with the TL431. So this is a adjustable voltage reference device. It's basically a Zener diode that you can control what voltage it has its reverse voltage breakdown on. So the way you control it is right at this point. This is the reference terminal. And so to quickly go over the device itself, internally it looks something like this. It has a comparator that has its negative terminal set to 2.5 volts exactly, and then this is the user reference voltage. And when your voltage exceeds 2.5, it will turn on a switch which will dump current down to whatever the bottom part of your circuit is, typically ground, and assuming this is this terminal here, so that's like the cathode. So whenever you exceed your reference, it starts dumping current, and as you can see up here, when you put a resistor here, that will put a greater voltage drop, and that's how it controls what's at its output pin. So that's how that works. And there's multiple ways you can configure the device. You can directly tie this reference to the cathode, in which case it just sets the output to 2.5 volts. Or you can set a resistor divider, voltage divider, same thing. And you can basically make it so that you need a higher voltage than 2.5 before it switches it off. And so the actual equation would be V out is equal to 2.5, 1 plus R1 over R2, where R1 is this upper one, I think. Can't remember if that's exactly right. They might be flipped, but R1 and R2 are here. So when you set them to be the same, it will give you 1 plus 1, which is 2, 2.5 times 2. So it's just nice. I don't have to think about it. It's just 5 volts, and that's the voltage we're trying to set because we're going to power the microcontroller with 5 volts. So, how does the rest of this work? So we've biased it so that once this line becomes 5 volts, this will start draining current to prevent further flow. So let's work in the rest of the circuit. So up here we have an NPN transistor, and we have the 6-volt line up here, 150 ohm resistor. So the way this essentially works is you have in an NPN, you can simulate it with a diode like this. So an NPN transistor behaves as if you had 2 diodes from base to collector and base to emitter. Oh, I have those flipped. Base to emitter, base to collector for an NPN. But what does that mean? That means that there's going to be approximately a 0.7 voltage drop, 0.8 voltage drop from the base to the emitter here. We want 5 volts on this line because this is the line that's going to power the microcontroller. So, in order for me to have 5 volts on this line, I'm going to need approximately 5.7 volts on this upper line here. Okay, so I'm going to explain this in 2 main scenarios. One, let's imagine that this line down here is not 5 volts right now, maybe it's 4 volts. So what happens when the line down here is less than your voltage? And maybe, it's ground on startup. So let's analyze the circuit. If this is less than 5 volts. Well, what we know then is if this is less than 5 volts, this is closed, because only when the reference at this point is greater than, or when this is 5 volts, does this reference turn on. So in that case, the switch is closed, meaning no current will flow through this device. So then if we look up here, if no current flows through this device, then we have 6 volts through a 150 ohm resistor to a base. So if you had very little current at all, there might be little to no voltage drop here. So then, if there's little to no voltage drop here, we could say it's still maybe approximately 6 even. Well, then you have 6 volts here, and because NPNs have this 0.7 volt diode drop, then you can see that we go from 6 volts here to 5.3 volts. So just with assuming little to no current, and if you had more current, then it might not be 5.3, you would lose a bit of voltage here. So it might be 5.2, 5.1, whatever. So continuing on, suppose this is 5.3. Now we're in the second scenario where the voltage on this line is higher than what's expected. So if you have 5.3 on this line, what's going to happen? Well, over here, you have exceeded 5 volts. So through this divider, you have greater than 2.5. So it's whatever, 2.6, maybe a little past that. Because the internal comparator is now 2.6 versus 2.5, the switch inside will turn on. So now this will start dumping current with little to no resistance. What does that mean? Well, we have 2 paths here in parallel. One is through the NPN transistor, and the other one is to this device. So if this device now is a parallel path with no resistance, what's going to happen? You're going to have more current flow, and it's going to flow down this device. Well, what happens when there's more current flow? Well, the voltage drop across the 150 ohm resistor increases. And so instead of having approximately 6 volts here, it's going to drop down. Maybe 5.5 volts is now at the middle point, or maybe 5.4. It's just going to drop as the current increases. And if it were to drop too low, maybe even if 5.5, for example, if it were to go there, now with this 0.7 voltage drop across, you have 4.8 volts. So then it cycles back again. Well, the switch turns off because it's 4.8 volts, which means that the current is very little here, meaning that this will start increasing its voltage again, which will cause it to go back up high. So in reality, this is going to reach an equilibrium point where you'll have, if this is 0.7, you'll have a 0.3 volt drop across this 150 ohm resistor. And I calculated it because the microcontroller will take 50 milliamps on like idle state, as what I read. So, I mean, if you were to calculate this, one with VIR, then if you have a 0.3 voltage drop across the resistor and it's 150, that is what? That's 1/5. Or it's not 1/5, but that's the fraction, and you multiply this by 1,000 to get milliamps. So what you have is 300 divided by 150, so you end up getting 2. And because of how BJTs work, any current going through here gets amplified, so we're assuming a gain of about 50. We have 2 times 50, which gives us 100 milliamps that this transistor is capable of providing. So that's why I selected 150 for there. I did that before showing you this. So that's how this works. Back to the main circuit. So we've established that this circuit will provide about 5 volts, which will feed into the microcontroller here. So that's just going to power the Nano. And the Nano is going to have 3 in-out signals. So the first one is right here. This is going to be a switch I put on my desk, which will be an indicator. It'll be binary, 1 or 0, which will tell the microcontroller, okay, turn on the switch or turn off the switch. That is powering the desk. So that's what this is for, and I'm just going to feed that directly to 6 volts. Or no, I'm sorry, I'm not going to, that's a terrible idea. 5 volts. Just so I don't damage the GPIOs. So 5 volts here for that signal. On the right side, we have another actual NPN transistor, which I'm using to cut on and off the load for the PWM. So I just thought, looking at this now, it doesn't seem as necessary, especially with a full power switch. But this is basically going to allow the microcontroller to basically choose whether or not it wants to power the servo motor. So it's another switch. Whether it's necessary, I'm gonna think on that. And then for here, this is the PWM signal that actually goes to the servo. So this is going to generate that frequency of 0.2 kilohertz to 1 kilohertz, and I'm going to have it selected here. The interesting thing is, if you put too much strain on the servo motor, it will have an excess of current. So the microcontroller, I don't really have a feedback system for that, so what I'm probably going to end up doing is just eyeballing it and seeing how much I can turn it before it puts like too much pressure on it and causes that current. So yeah, so this is the circuit, and what I'm gonna do is build this. I'm gonna verify this power section, set up this microcontroller, and get the whole batteries pack going, and try it out. The voltage is a little off, but given the variance in the resistors of the reference voltage, and the device itself also has a 1% offset, I'm sure it adds up that it's within those being at fault. So 5.1 should be good enough for the Nano, so I'm going to move forward with the microcontroller. Admittedly, it's been a while since I've used Arduino, but I just took their Blink example, switched to pin, and now I feel like I'm ready. So I'm gonna do the PWM signal now. So if I put 5 volts on, we get this fast switching frequency, and if I do ground, it switches to a slower one. So I mean, this is the principle of how the program is going to work when working with a servo motor. So with that out of the way, I think I can start wiring this up to the servo motor. Okay, so I'm going to power the Nano off of the battery pack and see if I can get it to work. So I just shift that over. Okay, it turns on, and it should still have the last program. So if I were to, the 5 volt pin's taken. If I were to just, I guess, probe ground. Alright, and then maybe 5 volt. Okay, perfect. So it's still working, and this is entirely off the battery pack, so that's a good sign. Okay, now I'll do the stepper. Okay, I uploaded it with the correct frequencies. I've wired the servo motor here, I even added a reversed out. I wasn't sure how inductive the servo motor load is, but everything is here, so I'm going to power it up for the first time and see if I can get the servo to correctly move without anything here smoking. Let me see if I can figure this out. Wait, hold on. What is happening? Why is it so erratic? Alright, I found the issue. It was software. It wasn't actually, the hardware was fine. I did add some extra things for it. Basically the frequencies were not in the proper range. Yeah, so now that I've fixed it, if I do go back and forth, we'll see the servo go actually to the full specs back and forth. So, with that out of the way, I need to actually, one, set up the power switch for the actual circuit. I need to actually attach it to the power strip under my computer. I need to tune it because going max values is not actually what I want. It needs to be just like barely going back and forth, so I'll need to fine tune that. But yeah, no, this is cool. What's gonna suck is if I have to get the values kind of right perfectly, otherwise I will turn off my computer while I'm trying to use it. So, all right. Okay, hello. It's kind of late while I'm recording this. I'm actually a bit ashamed that it's late for me. It's about 11. Normally I sleep way sooner, so. But I did some more mining off camera. I love mining off cam for whatever reason. My friend helped me model this 3D box, which has some areas for the wires of the PWM to go out, as well as some switches to power this thing, and it actually comes with a battery pack as well inside, and I can show you. This is for programming. I'm still working out those details, but if I switch this one on the bottom, you can see the light turns on for this, and if I were to hold the servo up and press this switch up here, you can see it's going back and forth. And this is, yeah, let me get out of frame so it, yeah. And that's just me toggling this back and forth. Turn power off. Yeah, so I still need to test this on the actual power strip. It may turn out that it does not have enough torque, which will be very sad, but I'm actually just about to test if this currently works. So instead of powering off my computer, I'm just gonna do this on this power strip down here. Okay, the servo, this is on right now. The servo's like here. So if I were to hold the servo down, I'm a little nervous that the box is it's gonna cause too much current, but we can try. So if I were to cut on power and then flip the switch, yeah! Oh, that's awesome. And then we do it the other way. Oh, I can't take it. Hold on, what if I... Okay. So, it's not strong enough. Or it needs to turn more. Okay, that's good to know. Test 2. I've stepped up the frequency by about 200 hertz, which I'm hoping is enough. It needs to go more. Both sides, actually. It's like there, but not quite. It's like, just needs that final extra push to get it there. Okay, so if I instead, the arm is a little too long and it gets caught at this point, so I'm gonna clip off the arms here. So I'll just do that right now. Okay, so it's very positional, because if it's sliding to the right, it just doesn't work. But if it's like right on that middle point, where it's centered, it flips it on and off. I have command strips and zip ties. Let's try to connect it to the power strip. Okay, so it was 1700, I'm bringing it to 1600. I'm also going to bring up the turn off frequency to 12, because I am terrified of, I'm terrified of it just freaking out. Okay. Okay, I am uploading it. Okay, it's armed. It's dangerous. If I'm gonna shut off my computer, and we're gonna see if it can turn off all the power on my desk and the lights, which is actually the whole point of this. The sucky part is if it doesn't work, that means I have to turn back on my PC and reprogram it, which is gonna be a pain. Okay, it's time. We'll just do it from here. So turn on the switch, and if I flip this on, let's go! Ah! It's worked. Ignore the lab light. It worked. Oh man. Hold on. I turn it back on. I flip the switch. Oh, man discovers light switch. Holy shit. That's awesome. Okay, yeah, so that's this project. I'm really happy with how it went. There's some problems with it. The switches are sticking out of the box and stuff and all that, but that was the first design housing that I really have done. My friend helped me, of course, but starting to do stuff like that is cool. The design itself is practical. I'm using it to solve a problem in my own life, which it's funny to call it a problem. It's me bending down, but anything to anything to home automate. But it was cool to like solve a real problem instead of I'm happy with the other stuff, but they're more interesting ideas to explore or something visual. This was like it's helping me. So yeah, still speaking of the visual one, still working on that. It's kind of taken a lull. I need to check in with my friend who was writing software, and I also need to design the PCB for that. But yeah, it's still pretty late, but I finished it, so I'm gonna go to bed now. Thank you for watching.